Okay. So we started the recording. So someone was just asking about class topics. Yeah. So next week, what we're going to do is we're going to come to class and I'm going to spend the 2 hours, literally the 2 hours of class, like just reviewing like everything we talked about weeks 1 through 6. Just I'm going to do one example. Like we're basically going to do like a practice midterm in class. Next week, there's no homework assignment. But what I'm going to do is I'm going to post a practice midterm for you, like as an online quiz in Blackboard, and you should take it as like as a way to help you study for the midterm. Okay. I'll talk in a lot more detail about the midterm next week, but just some like highlights. Like so the midterm is going to be open notes, open calculator, or open notes, and you can use your calculator. I would come to class and I wouldn't just like show up with your notebook. I would definitely make 1 or 2 pages of cheat sheets to help you for sure. And the way I structured the midterm is going to be like 10 questions. Each of the 10 questions will have multiple parts, but I'll end up grading like your best 8 of them. So like, for example, everyone, I think I've said this before, but like probability tends to be like the hardest subject. Like, did people find the homework to be pretty hard last night, or that was due last night?
Yeah, that's what I found a little challenging.
Totally.
Yeah, but with the recording that you had on there, kind of really did help. And like I told you, I wrote down notes and everything, and it kind of put everything together.
Good. So this, like for example, so the midterm will be 10 questions, and one of the questions will be a probability section, and like because I'll grade your best 8, if you're like, I just can't do that, you can skip that on the midterm. Okay. But if you answer more than eight of the 10 questions, I'll still grade your best 8. So there's no reason not to answer more than the 8 that I'll grade. Okay. So does anybody have any questions about the midterm there? And I'll get you prepped next week too. Like we'll definitely prep for it. I promise. All right. All right. So real quick. All right. So homework. So I can spend about 5 to 10 minutes on homework questions. So who had a question, and which one would you like to see me do real quick?
So if you scroll down, hang on, I think it's 4.
Yeah, I know I had 2 4s. So
yeah.
Is it 4A or 4B?
4A.
Okay, so this bloodborne pathogen one?
Yeah.
Or foreign bloodborne pathogens. Okay. So this one is kind of like I don't know if you guys remember, I did the ELISA blood test in class last week. This one is kind of like it. All right. So like, let me just do, yeah, I'll walk you through this one here real quick. So basically it comes down to this. The probability that it does detect the virus is 0.995. That's what that's what the homework says. So if 2 people take the test, all right, what is the probability that both tests correctly detect the pathogen? Okay. 2 tests are correct, okay, that they detect it. Well, this is probably the first is correct and the second test, because you want them both to be correct. And when you see the and statement in there, does anybody remember what that implies that you do?
Multiplication.
Yeah. So this is just 0.995 times 0.995. And whatever that is. Okay. So if you were to have 10 people correct, all right, 10 people take the test. Basically, you would end up doing 0.995 raised to what power?
10.
Yeah, because what you would do is you would go, the first is correct, and the second is correct, and the third is correct, and so on and so on and so on. Okay. So just curious, when you were doing that problem, did you have it kind of set up that way or no? Asking you, Ann.
Oh, I'm sorry. No, I definitely didn't.
How did you do it?
So let me pull out my notebook, just a moment.
Yeah, like these are really hard. Like, yeah, I wish I could tell you like there's an easier way, but like it's like the first is correct. And you would keep going till the 10th is correct. Like that's how you would approach that problem.
Yeah, I think that's where I'm always sort of like lost. I sort of always forget that I have to do it to, so where you said 0.995 to the 10th power, how did you get to that point?
So if you want 10 tests to be correct, right? So what has to happen is the first is correct, and the second is correct, and the third. And whenever you see and, that means you're going to multiply. And so that would be 0.995 times 0.995 10 times. So that's where you get to the 10th power.
Okay.
And then the at least 1 in 1,000. The last part, at least 1 in 1,000, is incorrect. Or doesn't detect, whatever.
Mhm.
That is just going to always be 1 minus the probability all 1,000 are correct. So that ends up just being 0.995 to the 1,000, 1 minus 0.995 to the 1,000th power.
I do have that on my notes from the Alyssa test.
Say that again.
We did that with the example from class, the Alyssa.
Yeah.
Okay.
Yeah, it's the same type of problem.
Okay.
And again, I'm always honest with you guys, right? Like this stuff is really like, it's just weird and it seems abstract and like, the only reason, like, obviously I've been doing this for 15 years or however long I've been doing this. So for me, it's like, oh yeah. Because I've been doing it for so long. Like, I don't beat yourself up if you're like, wow, this is a little hard to wrap my head around writing it, because we've like literally spent one lecture on it,
I sort of wanted to just practice it a little bit more, just until it registers in my head.
Yeah. So next week, what I'll do is when you see the when we do the practice midterm and then I post a practice midterm, you'll be able to practice it a lot. You'll see. Yeah, go ahead. Go ahead.
I was just going to say, is there like any website or anything that you could recommend where we could just sort of solve different types of problems with the same type of strategy, like probability?
Yeah, so the textbook is not great on this stuff here. If you email me, I will send you, and I can just post this in the classroom for everybody if you want under the class file. I can post like some of my old tests and you can try them. And then if you want, just email me your stuff and I'll look it over for you.
Okay.
That would be great.
Okay. Can I trouble you? Can you please just shoot me an email and say, hey, Matt, you can be as short and rude as you want. Like, Matt,
no.
You said in class to email to remind you, and then I'll do, yeah, I'll do that later.
I'll write a reminder to shoot you an email after class.
Say that again.
I'll write a little reminder right now on my notepad to send you an email after class.
There you go. And then I'll post it tomorrow. Okay. Class, I have to take care of the little guy.
Yeah.
All right. Okay, so I want to start the lecture today now. And don't stress so much about the notes because I am going to post the PowerPoint slides. Okay. So on your in class today, what I want to do is I want to introduce us to this topic called discrete random variables. Okay. The two things real quick. First, we're going to skip the break today. We're going to work right through. And I'm really sorry about this, but I have to end class at like 3:20. It's just like my wife and I are like, here's the kid, here's the kid, I have my Zoom call, you have your Zoom call. So I have to, you know, do you understand what I'm saying? Like it would be my time with them then. So I'm really sorry I'm going to shortchange you like 20 minutes. Okay.
That's fine, Professor. We know your son comes first. We got you.
Yeah, I just didn't want to cancel class today.
I'm gonna tell you like you tell us, don't stress it. It's your son, we got you.
All right, thanks, Cornelia. I appreciate that. Okay, so what we're going to spend our time talking about today is this concept of random variables. Okay. So in mathematics, if you guys could just maybe help me out just a little bit, like when you hear a variable, like what letter in mathematics do you associate with a variable?
X and Y.
X, yeah. So the first one, at least for me, and awesome, Manuel, like the first one that comes to me is like X, right? And so when you think of a variable, what in mathematics, what it kind of like hits home for me is like it's an unknown value, right? It's some unknown value. And like in algebra class, you would always solve for X. So what we're going to do is we're going to spend this week and then literally the first 2 weeks after spring break talking about this concept of random variables. And so in our class, the concept of a random variable is slightly different. And I'm always going to, and I'll say this, and I think I've said this before when I teach, like the first 20 minutes of class today is a lot of definitions, like this definition. And it's always weird at first, like, Matt, what are you talking about, Matt? And then once you see the first example in class today, I promise you, Dick, okay, all right, I get what you're saying. So just bear with me and keep that in mind that it will make sense as we go through. All right. So our first definition. A random variable. That's what we're defining. Okay, so in our class, in statistics, a random variable is a quantitative variable. If you guys wouldn't mind just muting when you're not talking for the background noise, I'd like really appreciate it. Okay, quantitative. So have we heard the word quantitative before in this class?
Yep.
Okay, in what context? Like, what does quantitative mean? So it's a data type, right?
It's a measuring.
Yeah, it's like a numerical measure of some type, like a numerical value measure of some type. So it's a quantitative variable whose value, so whatever value this variable, this unknown can take on, whose value is determined by chance. Okay, so like there's some like probability associated with the values that it could take on. Okay, so in our class there's going to be two types. Okay, so if you remember, this is like week 1 of the class. We had quantitative variables, and then there were two types of sub variables. One type started with D and one type started with C. It was like something counts and something was like measurements.
Excuse me, Professor. You said determine. What's that? Change?
Chance.
Okay.
A little bit of a chance. Do you guys remember the terminology discrete and continuous? Do you guys remember that?
Continuous, yeah.
You said discontinuous?
Discrete. So discrete.
Oh,
Did people remember what discrete meant? Like a discrete variable?
mhm.
It was, I think it was counts of some type. And continuous was like measurements of some type. Okay. So what we're going to focus on in our class today is these things called discrete random variables. Okay, so discrete random variables, what they have is these unknown values who are determined by chance. They have a finite number of outcomes or finite number of possible values. All right. So what I mean by that is, all right, we're going to have this unknown variable, and there's only so many things that could happen. Okay, like maybe there are 5 outcomes, maybe there's 2 outcomes, maybe there's 3 outcomes, but there's a finite number of possible outcomes. Okay, like let me give you some examples. All right. The sum of the results on 2 die rolls. So if you guys remember on the videos that you watched last week about probability, I talked about this casino game where you throw 2 dice and then you sum their results. Does anybody remember what casino game that was? So throw 2 dice and sum the results.
No idea.
It starts with a C. Craps. People remember? So like if you look back in the lecture slides, it's okay. But I did this probability experiment where you roll 2 separate 6-sided dice. You go, whoop, and whatever the outcomes come up, you add them together. So like if you roll a 2, then a 3, your result is a 4, or your result is a 5, and that's going to be living on in the recording forever. So that has a finite number of possible outcomes. Like there's only so many different combinations of die rolls you can make. Or like the number of games the World Series will last. Does anybody know what's the least amount of games the Baseball World Series can last and the maximum?
I think it's 5.
It's best of 7.
That's a 7, so it will be 5 and.
So the minimum number of games is 4 or 5 or 6 or 7. Okay, so that's what I mean by like a finite number of outcomes. There's only 4 outcomes here for the number of games the World Series could last. And like there's chance associated. Does it last 4 games, 5 games? There's a lot of things that go into it. All right, and trust me, as we go through the examples today, this will become more clear. And what we're going to do when we come back from spring break, okay, is then we're going to talk about something called continuous random variables. And so the thing that's about continuous random variables and why they're a little bit harder, they're actually going to be significantly harder than this stuff, is they have an infinite number of possible values. Okay. And that's where things get hard, when there's an infinite number of possible values. Like, let me give you an example of, something that will definitely work with here. If you were to take the height of a random chat now. For the person who sent me the private message, and I'm sorry to go off script here, it's on me. like, don't worry about it. I'm so sorry for the confusion. That's on me. You don't have to apologize. Like, again, like for everybody, like, I'm so sorry I had to switch to Zoom today. Like, this is, I hope you all can forgive me. Like, I'm really sorry about that. I know no one signed up for that, so I'm sorry. So the continuous random variable is the height of a randomly selected male in the United States. So adult male in the United States. Like, there's just an infinite number of different heights that somebody could have, possible heights. Is the male's height 5.5 inches or 5.5 feet, 5.05 feet, 5.555 feet? Like, it's just so ridiculous the number of possible options there are. Okay. So the highlights here to remember, okay, the important things. Random variable, we're going to deal with discrete. So there's a finite number of possible values, okay? And the values that come up they're all determined by chance somehow, all determined by chance. Okay. Is everybody okay if I go to the next slide? Everybody good?
Yes, Professor, you can move on.
Thanks, Jasmine. I appreciate it. But is everybody still alive with me today?
Yeah.
You guys find that it's hard to go from live to Zoom? You guys ever find that, like, it's the energy's a little bit lower?
Yeah.
Yeah, pretty much. Yeah.
All right. So I'm gonna try. So I bear with me. The first part of class isn't the most interesting, like, because I have to give you one more definition and then do some simple examples. But I promise you that at least the last few examples in class are rather interesting. I do promise that. Okay. So what we're going to do next is we're going to have, all we're actually going to do is get through two definitions today and examples. So the first other major definition we have is what's called a probability distribution. Okay. So you're going to hear this concept of a probability distribution a ton in the in the online lectures you watch this week, and then when we come back from spring break, it's just going to be a ton of this probability distribution. So all it is, a probability distribution for a discrete random variable that we'll call X. So we'll call our unknown value X. All it does is it provides two things. So this probability distribution, whatever this is, provides two things. One, it provides all the possible values of X. So first thing it's going to do is it's going to list all the values X could take on, okay? And what it also provides, if you look back here, I said the values that the random variable X can take on are determined by chance. Okay, so all the possible values X can take on and their corresponding probabilities. So it lists, basically what you're going to see is it's going to tell you all the values of X, and then, hey, what's the probability that X is 1 or X is 2, things like that. And in our class today, okay, the probability distribution can be shown as two things, okay? It can be shown as a table, which is what we're going to work on in class today, all right? And then the other way you can show it, okay, is with a mathematical formula. And that's what you're going to learn on your own this week, okay? And I do just want to say this, when you watch the videos on your own this week, do not get discouraged when you see this complicated formula put up there, do not. And I promise you that, you know, I'll show you, if you keep watching the lectures, you'll see me use your calculator and I make it a little bit easier for you, okay? Yeah, you came off mute. Did you have a question?
I'm sorry, I was just going to say, should we be writing this equation down just for reference?
So you can write down whatever notes you want from here. I am going to post the slides. So
Okay.
if you're like, if you just want to like pay attention, that's okay too. But when we start doing some of the examples, I would write those down, because like it's easier to wrap your head around stuff like when you're also writing it down, you know. But yeah, so I'm not going to show you any formulas, any mathematical formulas for probability distributions today. Today, literally for the next 50 minutes, it's just going to be about a table and then applications of that. That's it.
Okay.
Yeah. All right. So when we do these tables, and you'll see them in a second, okay, there's just some rules you need to follow. Okay. 2 rules. The first rule is the probability of any random variable, the probability of X taking on any value, it has to be between 0 and 1. So when I start writing tables, what that means is no individual probability can be less than 0, right? You can't have negative probabilities, or greater than a 1. So nothing can happen more than 100% of the time. Then the second rule does anybody remember what mathematical operator that it looks like a weird E, like what that means to do?
Summation.
Yeah. Okay. So the sum, if you sum up the individual probabilities for in this probability distribution, they all have to sum up to 1. So like whenever I write this table of values, you'll see in a second, all the probabilities have to sum up to 1. Okay. All right, so right now the correct response, like when you see this type of stuff, is to be like, what the heck? What are you talking about? A table with the X values and then the probabilities, like, Matt, what is this? Trust me, okay? So what I want to do now is I want to just show you some examples of probability distributions. That's it, okay? Is everybody okay if I go to the next slide?
Yes.
Okay. Thanks for the thumbs up and letting me know. Yeah, good, good, good. Okay. So these are just examples. I'm going to just put 2 simple ones up here, okay? And when we do these problems, you're going to notice the first thing I'm going to do is I'm going to define what X represents, what the random variable X represents. So I'm always going to write something like this. Let's let X be equal to, and then I'll write out what it is, okay? So I'm not going to tell you what this is. I'm going to give you the table first, and then I bet every one of you will be like, okay, I know what that is, right? So the table, this is what it does. It lists the possible values of X. And then in the next column over, it lists their corresponding probabilities. So think about this. What have we talked about in this class that the possible values are 1, 2, 3, 4, 5, and 6. And the corresponding probability you get a 1 is 1 out of 6. Probability you get a 2 is 1 out of 6, and so on. Can anybody tell me what that's a probability distribution for? We spent a lot of time talking about this when we were doing probability.
Die roll.
It's a die roll. Yeah. Yeah. So here's the thing. When I roll a die, I don't know what value is going to come up. Okay. I don't. I know it could be a 1, 2, 3, 4, 5, or 6, but I don't know like what number will show up. Right. And I think I tell this joke multiple times, but like if I did, I would still be living in Las Vegas. Right. Like my job would be at the craps table. Okay. But I don't. So X is going to be the result on a die roll. Okay. Yeah. And that's all. And that's what the probability distribution is right there. Hey, it's numbers 1 through 6 and their corresponding probabilities is, 1, 6, 1, 6, 1, 6, 1, 6, Let me give you another one, and I'm just going to make this one up. This is a little bit goofy. After I got out of college and I got my first real job and I had to get up early. What do you think, like most adults, I got addicted to?
Coffee.
Coffee. Every morning I drink so much coffee. Is there anybody else with me? Are there any coffee drinkers in here?
Yep.
Honest, I drink so much coffee. It's embarrassingly to admit how much I drink. Okay. All right. So let me define a variable here. I'm going to say, let's let X be equal to the number of cups of coffee Matt has in a day. Okay. All right, so what do you think is the least amount of cups of coffee I have in a day? I'm just curious. Like,
1.
close. So do you ever think there's, you're close. There are a few days when I have, actually when I have 0 cups of coffee. Okay. So that's the least. One is close. Like, let me give you an example. This happened last week. My son, who's always sick, makes us sick. And so he had a stomach bug last week from daycare. And so, he gave it to my wife and I, and like, I woke up and I'm like, I can't have coffee. Like, I will just throw it up. Okay. So like, sometimes I have 0. But then sometimes I have 1, 2, 3, and then I usually try to cut myself up after 4. I try. Okay. So look, let me just give you the corresponding probabilities of each. Very small odds, I have 0, so it's only 5%. 0.15 here, 0.25, 0.25, and 0.30. Okay. So look, to verify that this is a probability distribution, are the individual probabilities all between 0 and 1? Yeah. Yeah. And what can anybody tell me what all these probabilities actually sum up to?
1.
Yeah. And if you look here, that's it. Probabilities have to be between 0 and 1. And then when you sum up all the probabilities, they have to be equal to 1. So it's like, it works. Okay. So this is a probability distribution. All right. So I have great news for everybody now. All I want to do is give one more definition. And then from that definition, I just want to work 4 examples, and then we'll be done. Okay. And so this is what I do have to say. The first 2 examples are not the most interesting. Okay. But then the final 2 examples are like examples where you from the real world that makes you see how this is useful. Okay, like that. Like sometimes it's hard to see how this is useful. But then so we'll do two real, like really real world examples to bring this all home. Okay. Who is, okay, if I go to the next slide.
Yeah.
Yep.
Okay.
Yep.
And I saw that we just had one late arrival, and don't worry, I'm recording the lecture. So if you just hopped in, yeah, I'll post the recording for this later, so you'll be able to catch up. It's not a big deal. Okay. All right, one last definition for today. And this last definition is what's called the mean, or it's also referred to as the expected value for a discrete random variable. So the mean expected, sorry, I wrote expect value, expected, the mean or expected value for a discrete random variable is given by the following formula. And so what I mean by, the mean or expected value, I'm going to go back one slide real quick. It would be like I'd give you this table and I would say, hey, what is the average number of cups of coffee Matt has, to drink each day? What is the average? Okay. Or another interpretation is, hey, if I roll a 6-sided die, what number do I expect to come up? Okay. And I'll explain what that means in a second. So we just denote the expected value with this notation. We use the Greek letter mu with the subscripted x. So if you remember, the Greek letter mu stood for the mean, okay? Super simple formula, okay? All it is it's the sum. So it's the summation sign of each x value times their corresponding probabilities. That's it. So you're just going to take each x value, multiply by its corresponding probability, and sum them up. And that's it. Okay. So just a note, like what I mean when I say what is the average or expected value. The expected value for a discrete random variable is the long run average of repeated observations. Okay. So like the first one we're going to do is what is the expected value for a die roll? So like if you were to just take a die, okay, and you were to just keep rolling it over and over and like over and over and over again. So like you get a 1, then a 2, then a 3, then a 3, then a 6, and you kept doing this over and 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 over again. What would be the average die roll? That's all this is saying. Okay. So it's the long run average, long run average. All right. For now, formulas seem pretty simple. Not too bad. What do we think? I got one thumbs up. Everybody else is tired.
Not bad, Professor.
Thank you, Jasmine. I appreciate that. Everybody else okay?
I'm a little lost, but I think I'll get it.
You'll get there. Okay, so let's do the following, okay? Let's find the expected value, okay, for a die roll. Okay, so I'm gonna go to the next slide here. All right. So it goes like this. This is how you just give me 1 second. Give me 1 second. I'll step. I'll be right back in a second. One second. Sorry about that. Some of the issues working from home. Okay, so find the expected value for a die roll. Okay, so the first thing you're going to do, all right, step one, is you're going to write the probability distribution. Okay. So like, let's go back for a second. First thing you're always going to do is you're going to rewrite this entire distribution, okay, for these problems. So again, you're going to say let X equal the result on a die roll. And then literally you're just going to replicate the table. Okay. So 1, 2, 3, 4, 5, and 6. Okay. And what were the corresponding probabilities again for these?
1/6.
1/6 for all of them. Yeah. Yeah. All right. Then all you have to do is just follow the formula. Step 2. Okay, it's a piece of cake. So mu sub x is equal to, it's the sum of each x value times their corresponding probabilities, okay? So all you do is you go, take the first value, multiply by its probability. So you go 1 times 1/6. And then you add to it. You go 2 times 1/6. And you keep going to the next one, plus 3 times 1/6. Plus 4 times 1/6. All the way to 5 times 1/6. To 6 times 1/6. Boom. Now we just have to figure that out. Okay, so for this problem here, let's not reduce it, okay? So you go 1 times 1/6 is 1/6. Does anybody know what 2 times 1/6 is? What that gets you?
$64.
So 2 times 1/6 would be,
I thought you said 2 to the power. I'm sorry.
that's okay. 2 times 1/6, so you go 2 times 1 is 2, and then just divide by 6, you get 2/6. How about 3 times 1/6? What does that get you then?
Would it be 3/6?
Yep, and so on. And 4 times 1/6 would be 4/6, and then 5/6, The reason I left them like that and didn't reduce is because now they'll have a common denominator. And so now you can just add them, right? So you can go 1 + 2 is 3, 6, 10, 15. This is 21 out of 6. And this is cool. This is really cool. Can anybody with a calculator tell me what 21 divided by 6 is?
3.5.
Yeah, this is what's wild. Okay, what I'm saying here is that the average, the long run average of die roll is a 3.5. So can you look at that and can you actually roll a 3.5 on a die? Like, can I roll a die and a 3.5 come up?
No.
No.
You can't. But like, here's what's really interesting. That is still the long run average. Like, I can't roll a die and have it like teeter between a 3 and a 4. So the one thing I wanted to hint at here is like, it's okay when you do these problems and you get a number that is actually not a possible value. Like, that's totally normal, totally okay. All right. Like, for example, when 2 students take a test and one student gets a 79 and the other student gets an 81, like the average is still an 80, but no student actually got an 80. Like, it's okay that there is no actual value 3.5. Like, that's okay. I don't know. Was the formula, seeing it there, not too bad?
Gotcha.
It was
Okay.
good, Professor.
Yeah.
All right, let's go back then real quick. And let's do just for the number of cups of coffee I have, just so we're we can like figure out the formula here just for one more repetition practice. Let's find the expected value for the cups of coffee I have. All right, so let's just let's go through the formula. Mu sub x, it's the sum of each x value times their corresponding probabilities. You guys, you know what? You guys want to try this on your own real quick? I'll be quiet for 45
Yes.
seconds.
Yes.
Okay. See if you could try that. I'll be quiet for 45 seconds, 6 seconds. See if you can use the formula and got it. Anybody think they got it? I'm just curious. I'll give you another 10 seconds or so, 15. No rush though. The person who sent me the private message, yeah, that's the right answer. Very, very well done. Do you want to share? Yeah, right there. So let me show you, what to do here. So you're just going to go each X value times their corresponding probability. So it's like 0 times 0.05 plus 1 times 0.15 plus 2 times 0.25 plus 3 times another 0.25 plus 4 times 0.30. So 0 times that is 0. 1 times that is 0.15. I think 2 times 0.25 is 0.50. 3 times that is 0.75. And then 4 times 0.3 is 1.2. And yeah, if you sum those up, Jessica, awesome. 2.6. All right. So what do we think? Do you think you could handle one of these on the homework and maybe on the midterm?
Yes.
Yeah.
Yeah, if it's like that, yeah, I'm good to do it.
All right. So you'll notice like on your homework, like your first problem on your homework. Let me just show you. Homework. Like your first problem on the homework is exactly that. Okay. But then the second part of your homework, it's another expected value question, but it involves working a word problem and figuring out the word problem aspect of it. So all I want to do is I just want to get through 2 examples of like real world, like setting up these problems and figuring out the expected value and then interpreting them. Okay. Everybody okay if I go to the next slide?
I'm good.
So have you guys ever heard of this saying about a casino? The house always wins. Has anyone ever heard that saying?
Yeah.
What do you guys think that means when I say the house always wins?
They always get their money back.
Okay. So like, it's true. Yeah. But like, okay. So here's the thing. Can I go to the casino and can I have a good night and win a bunch of money if I go to the casino?
A possibility, yes.
Possibility. Yeah, sure. I've, there's been nights. So when the house refers to the casino. And so like, yeah, sure, I can go to the casino and make some money. But like the saying the house always wins means the house will always win in the long run. Okay. And so I want to explain to you with a casino game why that is. All right. So I want to work an example from a casino game. Called roulette. How many people have heard of roulette before? Just out of curiosity.
Yep.
Got a couple of, let me show you what a roulette board looks like, okay? Maybe if you've ever seen something like this in a movie or something like that, okay? So this is a type of roulette board we're going to talk about here, okay? So let me make that a little bit bigger for us, okay? So the way roulette works is the following, okay? They have this wheel, okay? And if you look here, and I know it's hard to see, but you guys see 3 different colors on the wheel? What are the 3 colors you see on the wheel here?
Black, red, and green.
Black, red, and green. Okay, so here's what happens. When you go to a casino and you add a roulette wheel, they take the wheel and they spin it, okay? And there's all these different numbers embedded in the wheel, okay? And they drop a little white ball in there and it spins and it spins and it spins. And eventually what happens is the white ball lands in one of these grooves in the number, and that's the number that comes up. In this table right here is how you bet on the wheel. And I'm going to talk about a very simple bet. Okay. So to simplify this, okay, there's all these different numbers around the wheel and they're not put in order. It's all random. And so you have the numbers 1 through number 18. Those are going to be our black numbers. I'm simplifying it a little bit. Okay. But like if you look here, some numbers are black. It's not 1 through 18, but I'm just simplifying it. Okay. And then you have the numbers 19 through 36. Those numbers are the red numbers. And then look at the wheel. Okay. Sometimes it's not easy to see, maybe like this wheel here. What other two numbers are on a roulette wheel? What are the green numbers?
00 and 0.
Yeah, and so there's two other numbers there. There's a 0 and a 00. Okay, and those are going to be our green numbers. Okay. So how many total numbers are there on a roulette wheel? There's the numbers 1 through 36, and then green, and then 0 and 00. So how many total numbers are there?
38.
There's 38. I'm just curious. I'm going to pause here. Has anyone ever played roulette? I'm not.
No.
No. It's actually, I'm not saying to go to a casino. It's actually kind of a fun. You can lose a lot of money quickly, as you can at any game in the casino. But it's kind of a fun game. All right, so here's the bet we want to talk about for this game. Okay. So what you can do when you bet on roulette is you can pick any single number that'll come up, and if it comes up on that number, you win big. But it's the most common bet you can make. Do you guys see this where my mouse is, where it's going over red and black? Do you guys see that?
Yes.
Yeah. So what you can do is you can put all your money on one of those colors. And if the roulette wheel ends on falls on one of those colors, you win, and you win what's called even money. So let me explain that. Okay. If you bet $10 on black and a black number comes up, you win $10. Okay, it's like, yeah, the number 3 came up. I win $10. Otherwise, you just lose your $10. Okay. Okay. So here's what we're gonna do. All right. Imagine I'm gonna go to the casino this weekend. Okay. I'm not really, but imagine I am, and I'm gonna go play roulette, and I'm just gonna bet on black. Okay. I want to compute the expected value for a $10 bet on black. Okay. So what I want to do is I want to compute the long run average. If I go to the casino, like what's going to happen in the long run. All right. If I keep betting on black. Okay. So this is an actual casino game. So do you guys think it's going to be, I would expect the average to be in my favor or in the casino's favor? Okay, Hannah has it. We would think it'd be in the casino's favor. All right. Everybody okay if I go to the next slide?
Professor, hold
Mhm.
on.
Yep.
After under red, what's that? That's a 0? What is that?
And double zero. So there's the numbers 0 and double zero. Like if you look here, you can see how it has 0 and double zero on the wheel there. That's
Yeah.
what I'm referring to there. Okay. All right, so let's do that. Let's compute the expected value and then let's talk about it. All right. So here's what's going on. When I go make the bet, my $10 bet, do I know ahead of time if I'm going to win or lose?
No.
I mean, I wish I would, but no. So here's what I'm going to do. It's random. So I'm going to let X be equal to the amount Matt makes betting on black. Okay. So I got to set up my table. If I'm going to bet on black, okay, and it's a bet, all right, I can win the bet, or what else could I do?
Lose.
All right. All right. Okay, good. All right, so if I win the bet, okay, remember, I'm doing a $10 bet. If I win, how much money does the casino pay me?
$10.
I make $10. Yeah. Now, if I lose, how much does the casino make off me? $10. So I'm going to put negative $10. All right, so now here's the thing. This is important. In the previous two examples we did, like all the numbers were in nice in a row. That doesn't have to be the case for these real world problems. Like, Matt, you either make $10 or you lose $10. Okay. All right, so now I need to figure out the probability I'm going to win the bet. All right. So looking at this, there's 38 total numbers. How many of the numbers are black numbers on the roulette wheel?
18.
Yeah, so what's the probability I would win then? $18 out of how many total numbers are there on the wheel?
38.
Perfect. Yeah. So then by extension, what's the probability I lose? Well, I would lose if a red number comes up, or what else comes up? I lose on red or green. So there's 18 red numbers and 2 green numbers. So the probability I lose would be 20 out of 38. Okay. So now look, the expected value on my bet. You're going to sum up each X value times its corresponding probability. So I'm going to take $10, multiply it by 18 over 38. And then I'm going to add minus $10 times 20 out of 38. All right. So watch this. Okay. Sorry for a little bit of background noise. My wife's got a little help with the kid, guys. So look, 10 times 18 gets me 180 out of 38. Plus, does anybody know what 10 times 20 is?
200.
200, so it's minus 200. All right, so What is 180 plus minus 200 get you?
$20.
Negative.
Positive or negative?
Negative.
Negative.
Okay, so watch. So this ends up being, this is wild. It ends up being negative 20 out of 38. Right. So let's grab our trusty calculator and see what that is.
It's a negative decimal.
Yeah. So remember, this is in terms of money. So I'm going to round it to 2 decimal places. So it's 0.53. So it's negative 53 cents. Okay. So this is what I'm saying. If I go to the casino, all right, if I go to the casino and I keep making this bet, my long run average of betting $10 on black, every time that I put $10 down, I expect to lose 53 cents. Okay. Is that good or bad for me?
Too much for me, Professor.
Yeah, me too.
Well, let me ask you this. Who's it good for?
The casino.
You know,
Yeah. So here's what's going on. So like, if you ever go to a casino and you see people like winning money and are very happy, like the pit bosses and the people at the casino, they don't care because they know in the long run, like, hey, people are going to keep playing roulette. And in the long run, you're just going to lose all your money to me. So like, great that you won now, but people are going to keep playing all night. And on average, we expect every time you bet $10, you're going to lose 53 cents. So that's crazy, right? Like there's no casino game you could go and play where you have positive expected value. Like they set all these games up so that like in the long run, people will lose, you know?
unless you walk away when you up. That's a
Yeah.
problem. People get too greedy. Once you get up, you guys just get up and leave. That's it. People just keep thinking, oh, I'm going to get more. I'm going to get more. And then you end up losing it all.
And I will say that that has happened to me multiple times. But anyways, a little bit more interesting than just like the average on a die roll, this right here. I hope it's a little more interesting. Okay. Don't stress. I will never ask a casino game problem like on a midterm or a homework because you know if no one's there to explain the casino game for you, it's a little bit confusing. Okay. All right. So I just want to do one last example here for you. Okay. And I'll say this, okay. This problem, if you're only like kind of half paying attention or we're on Zoom and stuff, like hone in on this one because this is our last one for today. And your homework problem is a lot like this. And I'll always ask a question like this next one on the midterm. Okay. All right, last problem for today. And this is a problem about life insurance. Okay. Does anybody have and I'm just curious, does anybody have a life insurance policy in the class?
Of course.
A couple people do. Yeah, I got one thumbs up. Yep. All right. So we're gonna talk about me for a second. Okay. So let me give you an example about my life insurance policy. So Matt has, we'll use me, Matt has a 1-year term life insurance policy. Okay, let's just pause for a second. What does that mean, 1-year term? Does anyone know?
It's for just 1 year.
Yeah. So my life insurance policy I have, it's a 1 year. It only lasts 1 year. So if I want to re-up my policy, I have to buy a new one. So my policy only lasts for 1 year. Okay. So Matt paid I paid $700 for a $250,000 policy if I die. Okay, so basically what that means is, look, I gave New York Life $700, and they said, look, if you die, your wife and child will get $250,000. Okay. So let me ask you this: if I live, how much money does the life insurance policy make? How much money does the company make?
$700.
Okay. And if I die, how much do they lose?
250,000.
Well, we'll actually talk about that in a second. Okay. All right. So here's the thing. I'm going to give you a little bit of extra information for this. Let's compute the expected value of the policy to the company, to the life insurance company. Okay. So I want to know, so this is what's interesting. So even though I paid them $700, okay, like when the life insurance company goes to put this on their books, like how much to value this for, they're not going to say that the policy they sold me is worth $700. Okay. Can anybody tell me why they won't say it's worth $700? Because what could happen? What's the worst outcome here for me and for the company? Yeah, and then they lose a lot of money. And here's the thing: there is a non-zero chance that I will not make it. Okay. So I've got to tell you now the probability that somebody like me dies and the probability that somebody like me lives. So if you go to Google, there are these things called actuarial tables. And so what people have done over time is they've priced risk and figured out the probability that somebody of a certain age, if they're in good health, will die. Right. So this is from the Social Security Administration. And look, for a male, I'm 40 years old now. That happened quick. Okay. Right here. The probability that a healthy 40-year-old male will live to be 41, or excuse me, this is dies. I'm sorry. Probability that a healthy 40-year-old male dies before turning 41 is this right here. It's 0.002581. Okay, so it's low, but non-zero. Can anybody tell me then how I could figure out the probability I'll live to be 41? If I know the probability I'll die? It's just 1 minus this, right? Because that's the complement, right? The opposite of dying is living. So 1 minus 0.002581. So the probability I'm going to live, knock on wood, to be 41 is 0.997419. Okay, not pretty good odds. Okay. So now we can figure out how much the expected value of this policy is. So what we're going to do is we're going to let X be equal to the amount the company makes. So the best outcome for this is that I live, okay? If I live, how much money does the insurance company make? Well, how much did I pay for the policy?
700.
Yeah, they make $700, right? If I live, the insurance company makes my premium. They make the $700. And look, this is the probability I live right here. 0.997419. Now pause for a second. If I die, while the company will write my wife a check for $250,000, how much money does the company actually lose?
Did you add the 700 to the 250,000?
You're close. So they're going to lose. They're going to write a check. You're so close. They're going to write a check to my wife for $250,000. But I have already paid them $700, right? Like they're already plus $700. So all they're really going to lose is that, well, they already have my $700, but they're going to write my wife a check for $250,000. So they're really only going to lose $249,300. Okay. Like you have to take your premium and subtract away how much the payment is to find out how much they really lose, because they already have $700 in mind. So they're going to lose $249,300. And the probability I die is this small number. So the expected value of the policy, again, it's just the sum of the X values times their corresponding probability. So you take 700 times the probability I live, 997419, plus, if I die, they lose minus $249,300 times this probability I die. So watch, grab your trusty calculator here. Look what I'm going to do. I'm going to go 700 times this. Plus minus, so that's just minus $249,300 times the probability I die. And the life insurance company, even though I paid them $700, will only value this policy at $54.75, because that's the long run average. Because when they sell enough of these policies, eventually, this is sad, someone will die. But the average of all the policies they sell, they expect in the long run selling me this policy to make $54.75. So should the life insurance company sell me the policy? Like, is it a good thing for them to sell me that policy?
Yes.
Yeah, why is it a good thing for them to sell me the policy? Like,
Well, 'cause
go on ahead.
yeah,
Go on ahead. Yeah.
they'd be able to make money off of it, no?
Yeah, and they expect to make money. Like if they had done, like, this is how people price these policies. Like they don't want to price it so that people lose money, right? Like if they were to price a policy and have negative expected value, that would be really bad, right? So they want to price a policy so that they expect to make money, but also have it be competitive in the marketplace. So like this is the math that people do, like to figure out like how much should we charge to make a little bit of money, you know, and be competitive. It's interesting, you know. You did a little actorial accounting today, everybody, with this. All right, I have to end class. I got to take over. So I got to end us a little early today, if that's okay. I will post the recording. Let me stop there. I'll post the recording after class. I'll probably get to it tomorrow.